Hello friends, welcome again to discuss few fundamental questions related to structural analysis, and I am Dr. Nitin Naik from the Department of Structural Engineering, Sanjivani College of Engineering, Kopargaon. Friends, in the last video we have discussed around 10 questions related to fundamentals in structural analysis. Now this is the second video. Again in this video we will discuss few more questions related to fundamentals in structural analysis. Now let us start with question number 1. What are the internal forces developed in a beam when it is subjected to external load? So the answer of this question is there are three internal forces developed in a beam when external load is acting on it. So the forces are shear force, axial force and bending moment. If you consider a beam, simply supported beam, carrying some external load. Now if you cut the beam at any section, if you cut the beam at any section, then at the section where the beam is divided into two separate portions, to maintain the equilibrium you have to apply these three forces: shear force, axial force and bending moment. So these are the internal forces which are now exposed because of this cut, and these internal forces are shear force, axial force and bending moment. These forces maintain the equilibrium of the left side portion of the beam. And hence the correct answer is when a beam is subjected to external loading, the internal forces developed in the beam are axial force, shear force and bending moment. In structural analysis, while analyzing a beam, normally we are ignoring the axial force. We are considering only shear force and bending moment. But the correct answer is there are three internal forces: shear force, axial force and bending moment. Next, match the following pairs or match the pairs. So in the left side column, maximum deflection, values of maximum deflections are given, and in the right column, the type of beam is given. So first is PL cube upon 3I. So PL cube upon 3I, its answer is cantilever beam with point load at the free end. So actually friends, these are the standard formulae. When a cantilever beam which is fixed at one end and free at the other end is carrying a point load at its free end, then the beam deflects like this and B move to new position, that is B dash, and this is deflection at free end. This is the maximum deflection which is equal to PL cube upon 3I. Hence the correct option is D. Hence the correct option is D. Now in the second case, the maximum deflection value is given 5 WL raised to 4 upon 384 EI. Now the correct answer is A. Simply supported beam with UDL over the entire span. When we consider a simply supported beam like this, carrying uniformly distributed load over its entire span, so this is UDL acting over the beam. The beam deflects with convexity downward, and the maximum deflection occurs at the center of the beam, and this value is equal to 5 WL raised to 4 upon 384 EI. This is the maximum deflection. Third one is WL raised to 4 upon 8 EI. Now this, for this deflection, this is the maximum deflection when a beam is carrying uniformly distributed load over the entire span. Now instead of this point load, if UDL is acting over the beam, then the deflection at the free end of the beam, this is the maximum deflection, is equal to WL raised to 4 upon 8 EI. And the last one is WL cube upon 48 EI. The correct answer is C. This is the maximum deflection when a simply supported beam is carrying a central point load like this. This is simply supported beam supported at say A and B and carrying a central point load of magnitude W. Now here the beam deflects with convexity downward again. The maximum deflection occurs at the center below the load and the value is WL cube upon 48 EI. So in this way we can match the correct pairs for maximum deflection and for type of beam. Third one is find the degree of static and kinematic indeterminacy for the frame shown in figure. Now static degree of indeterminacy is related to the external reactions. Here I have not written the static degree of indeterminacy. It is denoted by DSI, and since it is external, it is related to the reactions. We can suffix E is equal to capital R, where capital R is number of unknown reaction components minus available equilibrium equations. Now in this case, let us calculate the unknown reactions. So this is hinge support. There are two reactions. This is again a hinged support. There will be two reactions. Thus there are four unknown reactions. There are four unknown reactions and the available equilibrium equations. Now we are having three available equilibrium equations, namely summation fx is equal to 0, summation fy is equal to 0 and summation m is equal to 0, and hence this particular frame is statically indeterminate with external degree of indeterminacy is equal to 1. Once the reactions are known, we can plot SFD and BMD for the given frame, and hence the frame is internally determinate while externally it is indeterminate to degree 1. While degree of kinematic indeterminacy is nothing but number of unknown joint displacements. Now for this case, we have to consider the unknown joint displacements. It may be displacement or deflection at a joint or rotation at a joint. So this is hinge support. If you consider the frame, it will bend like this. Let us assume the shape of the frame subjected to bending like this. So how many unknown joint displacements are there? So first one rotation at this support. So this is one. Then this joint, it rotate as a whole. So if you draw tangent to the elastic curve, the angle between the tangents is equal to 90 degree. Only one rotation is possible at this joint. So one rotation, 1 plus 1, 2. Again at this joint, there will be one rotation. These are the moment resisting joint, rigid joints. So one rotation, the joint rotate as a whole, and one rotation at this support. One rotation at this support. So 1, 2, 3 and 4. Four rotations are there. Plus this frame is subjected to sway because of this horizontal load. So side sway is there. Suppose this is point C. Point C will move to new position C dash. Here I will draw a figure for better understanding. So here C will move to new position C dash and this displacement is called as sway, and thus there are 1, 2, 3, 4 and 5. 5 unknown joint displacements are there, and hence degree of kinematic indeterminacy is equal to 5. One rotation at each intermediate joint and support and one sway. So thus there are 5 unknown joint displacements and hence degree of kinematic indeterminacy is equal to 5. Next, what is the significance of moment of inertia in case of a beam? Normally in practice we are using rectangular beams. We are using rectangular beams like this. width B and depth D. So B is less than D and moment of inertia is equal to 1 by 12. Moment of inertia denoted by I about the axis of bending is equal to 1 by 12 B into D cube. Now I am talking about rectangular beam, 1 by 12 B D cube. What is the significance of this MI? So moment of inertia reduces the deflection of beam. How it reduces the displacement of beam? If you go back to question number 2, this is question number 2. All these are the values of maximum deflection. PL cube by 3I, 5WL raised to 4 upon 38 EI. So at the denominator, I is there. At the denominator, I is there. So if you increase the value of I, automatically the deflection will reduce, and this is the significance of moment of inertia. So moment of inertia, it affects on the deflection. Higher the value of Mi, lower will be the deflection, and which is very important for structural stability and safety. So this is the significance of Mi. More the Mi, less will be the deflection. This is why we are using rectangular sections for beam in practice. Let us move to the next question. Draw influence line diagram for reaction at A. So this is the beam given A and support B. Reaction at A and reaction at B. So this is influence line diagram for VA. It shows that for a beam under consideration, when the unit load is acting at A, so this is a rolling load, moving load. When the load is at A, entire load will be taken by this support. So reaction at A will be equal to 1 and reaction at B will be equal to 0. And hence this is the ILD for VA. This ordinate is equal to 1 and at B the ordinate is equal to 0. Influence line diagram is a diagram which shows variation in quantity with respect to the position of the rolling load having unit magnitude over the beam. So it shows that when unit load is at A, the reaction at A is equal to 1 and the reaction at B is equal to 0. Okay, as the load moves from A to B, the value of reaction at VA, the value of reaction at A, it changes. So these are the values of reaction at A. When the unit load is at this position, this will be the value of reaction at A. Similarly, this is influence line diagram for VB. Here the maximum ordinate is at B. When the unit load is at B, the reaction at B is equal to 1. At the same time, when the load is moving from B to A, the value of VB, it changes like this. Okay, so here when the load moves from A to B and the value of reaction at A, it changes. When the unit load, it comes to B, here the value of reaction at A will be equal to 0. This is the meaning of ILD. This is influence line diagram for shear force at C. This diagram can be plotted like this. This is point C. First we have to plot influence line diagram for reaction at B below the baseline like this. Then we have to plot influence line diagram for reaction at A above the baseline like this, and then draw a vertical line through C. Okay, and this is the resulting influence line diagram for shear force at the section. There is a procedure, you can find this procedure in any book, and this is influence line diagram for bending moment at section C. So this is the correct answer for the given question. Now question number 6. Which of the following statements is are correct for the truss shown in figure? So 5 options are given here. First option is the magnitude of the forces on the link AB and DE. So AB and DE are equal. The link AE carries zero force. The link AE, where is AE? This is AE, carries zero force. Link CD and EB, this is zero force member. Link CD and EB, so this is CD and this is EB, experiences unequal forces. Link CE is in tension. Link CE is in tension. So to calculate, to find the answers for this question, we have to solve this truss using method of joint. Okay, so this is the solution. This is the solution, right? Which of the following statement is are correct? So the magnitude of the forces on link AB and DE are equal. So we have to solve the truss. We will solve it like this. Suppose this is the given truss. These are the reactions. Reaction at D, reaction, horizontal reaction at D, vertical reaction at A. This is free body diagram. These reactions can be obtained like this. Summation Fx is equal to 0, Ht is equal to 2. Summation M about D is equal to 0. You can calculate Vd. Vd is equal to 1. Now, using the condition for zero force member, we know when three members are there or three forces are acting at a joint, of which two are collinear, third be at an angle, then the force in the third member is equal to 0. So AE is a zero force member, and that's why the this statement is correct. This statement is correct. We'll check it. So first answer is this statement is correct. The link AE carries zero force. Let us move further. Now let us consider equilibrium of this joint D. Now after knowing Vd is equal to 1 upward, Va is equal to -1 downward. Okay. After solving this equation, you can calculate Va is equal to -1 summation Fy is equal to 0. Hence Vd is equal to 1. Now we consider equilibrium of joint D. This is joint D. Equilibrium of joint D. This is free body diagram. Summation Fy is equal to 0 and hence FDC is equal to -1.4142 kilonewton. Summation Fx is equal to 0. If you apply this condition, summation Fx is equal to 0, FDE is equal to -1. Compression. Negative sign shows compression, positive sign shows tension. Okay, FDC is equal to -1.414, FDE is equal to -1. So let us check the options. CD and EB experiences unequal forces because here CD is involved. CD is involved. So CD is -1.4142 and along with CD we have to calculate force in EB. So to calculate force in EB we will consider free body diagram of joint B. Free body diagram of joint B. So these are the forces acting on B. Okay, we know to satisfy the equilibrium force in AB it must be equal to 1 kilonewton because this is zero force member. To balance this VA, this force must be equal to 1 kilonewton. FAB is equal to 1 kilonewton. Sorry, VA is acting in downward direction actually. VA is acting in downward direction. Let me correct it. And hence, this is force in AB to satisfy the equilibrium 1. So this is FAB 1 kilonewton, FBC assuming it as tensile in nature, and this is FBE. If you apply summation Fy is equal to 0, -1 minus FBE sin 45 is equal to 0, FBE is equal to -1.4142. So let us go to the option. link CD and EB experiences unequal forces. Link CD and EB experiences unequal forces. But here the forces are equal in magnitude. So this statement is not correct. This statement is not correct. This is wrong statement. This is wrong statement. Okay. So two statements are studied. First, this is the correct statement. This is the wrong statement. Now we will consider one more statement, or let us further move the analysis. Okay. Joint C or joint E. We can consider equilibrium of joint C or joint E. Now if you consider this equilibrium, summation Fy is equal to 0, FCE, summation Fy is equal to 0, see, minus FBE into sine of 45. FBE is compressive in nature, so compressive. FBE into sine of 45 plus FCE is equal to 0. Okay, and hence FCE is equal to, take this term to the right hand side, FBE sine of 45, but FBE is equal to minus. Therefore, minus 1.4142 into sine of 45. The answer will be minus 1 kilonewton. It shows that CE is in compression. So, link CE is in tension. This is again a wrong statement. This is again a wrong statement. Now, the magnitude of the vertical reaction at D is equal to 1 kilonewton. That we have calculated. Vertical reaction at D is equal to 1 kilonewton. Therefore, this statement is correct. This statement is correct. Now, only one statement we have to verify. The magnitude of the forces on link AB and DE. AB and DE are equal. Let us check. Force in AB is 1 kilonewton. Force in AB is 1 kilonewton, and that in DE, we have to check DE. What is the force in DE? So let us check force in DE. We have calculated it. This is force in DE is equal to 1 kilonewton. Force in AB is 1. Force in DE is 1. Nothing is mentioned about the sense of the forces, only magnitude is mentioned. So force in link AB and DE both are same, and therefore this is also a correct statement. So out of these 5 statements, 3 statements are correct. So to find the answer of such questions, you must know how to analyze a truss using method of joints. This is the solution. You can take screenshot if required. Seventh question. Calculate distribution factors at joint B and joint C. So distribution factor, we know this is the formula for distribution factor, stiffness upon summation K. So distribution factor at B two members are connected, BA and BC. So stiffness for BA, far end is fixed 4EI upon L. Stiffness for BC, far end is simple or overhanging 3EI upon L. And therefore distribution factor at B for member BA is equal to KBA upon sum of distribution factors meeting at joint B. So summation is 7 EI upon L and KBA is 4 EI upon L, and therefore the distribution factor for BA is 0.57, and that for BC must be equal to 1 minus 0.57, so 0.43. Distribution factor at C, this is the overhanging simple support. There is no support beyond C to this side, and hence for CB the distribution factor is equal to 1, and the distribution factor for CD is equal to 0. This is a typical case. So these are the answers. Question number 8. Write formulae for fixed end moments for the beam shown in figure. So these are the standard cases. These are the standard cases, and we know when a fixed beam is carrying central point load, the fixed end moments at A and B will have the nature like this, and hence MAB or MFAB or MA only is equal to WL by 8 and minus WL by 8 at B. Minus sign because of this is clockwise, this is anti-clockwise. This is Hardy cross sign convention. For a beam carrying uniformly distributed load over the entire span, fixed end moment at A is equal to WL square by 12 and that at B is equal to WL square by 12 having opposite signs. Hence plus minus signs are given. For a fixed beam carrying a point load not acting at the center, the fixed end moment at A is equal to WAB square upon L square and that at B is equal to, since this is clockwise, minus W A square B upon L square. So this is the correct answer for question number 8. Question number 9. Find degree of static indeterminacy for the beam shown in figure. So this is the beam fixed at A, fixed at B, and there is a internal hinge at C. Now please read this statement carefully. If a fixed beam has an inclined loading over it, then the degree of static indeterminacy will be equal to 6 minus 4 is equal to 2. How? If suppose this beam is carrying inclined loading like this, then definitely there will be horizontal reaction at B, there will be horizontal reaction at A, vertical reaction at A, this is vertical reaction at B, and this is fixed moment at A, this is fixed moment at B. So how many unknown reactions are there? How many unknown reactions are there? So 3 reactions at this support and 3 reactions at this support. So degree of static indeterminacy, external, I am talking about external, is equal to number of unknown reaction component minus available equilibrium equations. Now available equilibrium equations are 3 in numbers. Summation fx is equal to 0, summation fy is equal to 0 and summation m is equal to 0. But for this beam, since there is an internal hinge at C, it adds one more equilibrium equation, summation m at C is equal to 0, and thus we are having 4 equilibrium equations and total reactions are 6 in numbers. So 6 minus 4 is equal to 2, and thus we are having degree of static indeterminacy external is equal to 2 when inclined loading is acting. But when inclined loads are not there, then what will happen? Now suppose this inclined load is removed. Now instead of this load, now I will add vertical loading only on the beam like this, maybe a UDL. Okay. Now what will happen? Because of this loading, now there will be no horizontal reactions developed in the beam. So this is equal to 0, this is equal to 0, and hence total number of unknown reactions are now, I will remove this horizontal reaction. Total number of unknown reactions now we are having for this end, there are 2 reactions at A, 2 reactions at B because of the vertical load. So total reactions are now 4. Total reactions are now 4. Now available equilibrium equations. Now available equilibrium equations, since there is no horizontal reactions, now only 2 equilibrium equations we should consider, namely summation Fy is equal to 0 and summation M is equal to 0. So two equilibrium equations are there, plus additional equilibrium equation is there because of hinge at C. So thus we are having 3 equations. So 4 minus 3 is equal to 1. So in this way you should write the answer for this question. Available equilibrium equations are 3 in general plus one additional equilibrium equation is there. That equation is summation of moment at C equal to 0, 3 plus 1 4. If inclined loading you are considering, if only vertical load is there, then 2 plus 1 So in this way we can write answer for this question. And now this is the last question. Knowing that for the cantilever beam shown in figure, the deflection at B is equal to 33.75 upon EI in downward direction. If the cantilever is propped at B, determine the prop reaction. Now here the beam will deflect like this. So this is YB and this YB is given 33.75 upon EI when the beam is not having a prop. But when prop is provided, calculate the prop reaction. This is the problem. So here first figure is without a prop. First figure is without a prop and second figure is with a prop. So I will read these contents. When the cantilever is propped at B, YB will be equal to 0. But due to the load in the first case, that is in this case, YB is equal to 33.75 upon EI. YB is equal to 33.75 upon EI. This is YB. Deflection at B. Okay. Downward direction. This deflection I will indicate as YB1. Now to have YB is equal to 0, the deflection at prop, that is at B, must be equal to 0. Must be equal to 0. Due to RB, this is deflection due to RB. And it must be equal to 33.75 in upward direction. In upward direction, that is YB2. And hence, when you apply a prop to this beam, I will just go to the sketch again. I will erase it. When you apply a prop at B, now this is the case, 20 kilonewton. Now because of prop, YB must be equal to 0. When prop was not there, YB is equal to downward 33.75 upon EI. To have YB is equal to 0, the deflection because of prop must be in upward direction and it must be equal to 33.75 upon EI. So YB1 plus YB2 must be equal to 0. Now here we will use the standard case. When a cantilever is carrying point load at its free end, the deflection is equal to PL cube upon 3EI. Now let us consider a prop only. I am not considering the 20 kilonewton load. This prop is applied at B and this is YB. This is YB is equal to PL cube upon 3I. Replace P by RB and L is equal to 1.5 in our case. And hence YB2 must be equal to YB1. Now YB2 is in upward direction, YB1 is in downward direction. Both must have equal magnitude. If they are having equal magnitude, resultant deflection at B will be equal to 0. So YB2 is equal to YB1. YB2 is RBL cube upon 3EI is equal to 33.75 upon EI. Solving this equation, we can have RB is equal to 30 kilonewton. So in this way, reaction at B can be calculated for the given beam. So you must know how to calculate the prop reaction to answer this question. Thank you.